In this video, I'm going to talk to you about the coordinates of a vector in a given basis. In general, the coordinates of a position vector to a particular point tell us what combination of basis vectors we need to add to get to that point. For example, here we've got a position vector x which runs to the point 2, 4, and on our diagram we've got the standard basis drawn in. The standard basis just consists of two vectors in R2. There's I, which is 1, 0, that just runs in the right direction, and then there's j, which is 0, 1, and that just runs in the upwards direction. To represent x in terms of the standard basis vectors, we can go twice along I and then 4 times along j. And that's what we put in the components of x. The first component says how many of the first standard basis vector we used. Well, we used 2 of those. We used 2 copies of I, so 2 goes in the first component. And then the second component says how many of the second standard basis vector we used. Well, we used 4 of j, 4j, so 4 goes in the second component. Now, the standard basis here is a pretty simple basis. For any position vector to a point in R2, the first component will always tell us how many copies of I we're using, and the second component will always tell us how many copies of j we're using. So the first component of the point becomes the first component in the vector, and the second component in the point becomes the second component in the vector. Pretty straightforward, right? Now, suppose we didn't want to use the standard basis. Suppose we wanted to use a different basis, say this basis here, b, which consists of the first basis vector, which is 1, 1, that's different from the original first basis vector, which was originally 1, 0, and then a second basis vector is 0, 1, and that's going to be the same one as before. So the first basis vector is what we're switching up here. So how does this change the coordinates of our vector x? Well, let's start by looking at how x can be represented in terms of these basis vectors. Like before, we're still going twice along the first basis vector, b1. That'll take us towards the right, to get to the right towards our point. But now with this new basis vector, we're not just going towards the right, we're also going up because there's also a 1 in the second component. So when we go right twice along that first basis vector, not only do we go right 2 times, but we also go up 2 times, and we end up at the point 2, 2. And then that's where we start using our second basis vector. Since we're already up 2 units, we only have to add the second basis vector 2 times. So 2 of the first basis vector, then 2 of the second basis vector. So now in this new basis b, since we're adding 2 of the first basis vector, 2 goes in the first coordinate of x, and then since we're adding 2 of the second basis vector, 2 also goes in the second coordinate of x. This is a little bit different from before. Before we had 4 in the second coordinate of x, but now we have a 2, and the reason for that is that we've changed our basis. So the main takeaway here is that if you change the basis, the coordinates of a position vector relative to that basis are no longer necessarily the coordinates of the point to which the position vector points. Here the point is 2, 4, but relative to this new basis b, the coordinates of x are 2, 2. And that's because the coordinates of x are really referring to the basis vectors. They're telling us how many copies of each basis vector we have to add to make x. Alright, so this new basis wasn't too tricky, but how do we compute the coordinates of a vector relative to any given basis? Here's an example where we want to find the coordinates of the vector x, which in the standard basis has components -3 and 5, and we want to find the coordinates of that vector relative to this new basis b, which has as its first basis vector 3, 2, and as its second basis vector -2, 1. So let's say that this vector x relative to the basis b has components x1 and x2. Our goal here is to find what are these components. What is x1 and what is x2? Well, we can start out by writing what this statement actually means in terms of the given information here. So this statement actually means that the vector x in the standard basis can be represented as x1 of the first basis vector in the new basis plus x2 of the second basis vector in the new basis. So now we can plug in some of the given information here. The vector x in the standard basis should be -3, 5, so we'll put that in over here. And then the first basis vector in our new basis is 3, 2, so plug that in for b1. And then the second basis vector in our new basis is negative 2, 1, so plug that in for b2. Now it just remains to solve this equation for x1 and x2. And a simple way to do this is to first convert it to a matrix equation. We'll keep this side the same. This is negative 3, 5, but then this side on the right, we can say that as a matrix, the matrix 3, 2 in the first column, and then negative 2, 1 in the second column, times the vector x1, x2. And we already know a way to solve this kind of equation. We can just use an augmented matrix. So let's set up our augmented matrix. On the left-hand side, we'll put our coefficients in our matrix here, 3 and negative 2 in the top, and then 2 and 1 on the bottom. And then we'll draw a line, and then the right-hand side will be the constant on the other side here, negative 3, 5. Negative 3, 5. There we go. So now we'll just reduce our augmented matrix using row operations. We want to get 1s on the diagonal and 0s elsewhere. So the first thing that might pop out to you is we can eliminate this negative 2 in the top row by adding twice of the bottom row. So let's do that. We'll write our new augmented matrix up here, and then we'll take the top row, row 1, plus twice the bottom row, r2. And our new augmented matrix then will be, well, the top row is 3, then plus twice the bottom row. 3 plus 2 times 2 is 3 plus 4, that's 7. And then negative 2 plus 2 times 1 is just negative 2 plus 2, which cancels out. Good, that's what we wanted. And then negative 3 plus 2 times 5 is negative 3 plus 10. Well, 10 minus 3 is just 7. Awesome. And then bottom row stayed the same. 2, 1, 5. Now to get a 1, 0 in the top row, we can simply divide by 7 here. So next move, we'll do r1 divided by 7. And that'll give us, in our top row, we'll just have 1, 0. And then 7 divided by 7, that's also 1. Okay. And then bottom row stays the same. 2, 1, 5. So now we've got a nice diagonal of 1s. We've got a 0 on top. And the only thing left to do is to get rid of this 2 on the bottom here. We want to convert that to a 0. So what we can do here is we can subtract twice the top row from the bottom row. So one more row operation, and we'll do row 2 minus 2 row 1. And the result from doing that, well, 2 minus 2 times 1 is 2, and that cancels. So 0. And then 1 minus 2 times 0 is just 1. 1 minus 0 stays the same. And then 5 minus 2 times 1, 5 minus 2 is 3. All right, and then top row is the same, 1, 0, 1. And this tells us our solution here. x1 is just equal to 1 here. x1 equals 1. And then x2 is just equal to 3. So there we have it. The vector x relative to the basis b, its components are just, well, x1 is 1, and then x2 is 3. There's our final result. Just to be sure, we can also check our result. This is saying that if we add 1 of the first basis vector and 3 of the second basis vector, we should get our vector x in the standard basis. So let's do that. Let's add 1 of the first basis vector, so 1 times 3, 2, and then plus 3 times the second basis vector, which is negative 2, 1. So let's simplify that. That's just 3, 2, and then plus the vector 3 times negative 2, negative 6, then 3 times 1 is 3. And then if we add these two vectors together, 3 plus negative 6, well, that's just negative 3, and 2 plus 3, that's just 5. And yeah, that matches up with what our standard form of the vector was, negative 3, 5. Perfect. Here's another example. Here we're given a basis B, which consists of two three-dimensional vectors. The first one is 1, 0, 2. The second one is negative 3, 2, 1. and we're also given a vector x whose components relative to the basis b are 3 and -5. So this vector is in span of b, and we want to find the representation of this vector x relative to the standard basis. This problem is a lot simpler than the previous one, because if we're told that the components of x relative to the basis b are 3 and -5, that tells us how many of the first and second basis vectors we need to add to get the representation of x in the standard basis. The first component here is 3, so that tells us we need 3 copies of the first basis vector, and then the second component is -5, so we need to subtract 5 copies of the second basis vector. And we can just substitute in for the first basis vector, 1, 0, 2 in here, and in the second basis vector we can also just substitute in -3, 2, 1, and then it just remains to compute. So let's go ahead and compute what x is relative to the standard basis using our formula that we've got here. So that's just equal to 3 times this vector, so that's 3 times 1 is 3, 3 times 0, 0, 3 times 2 is 6, and then minus, 5 times -3 is -15, and then 5 times 2 is 10, and then 5 times 1 is just 5. And we'll go ahead and subtract. So here we've got 3 minus -15 in the first component. That's really 3 plus 15 because the negatives cancel, and we've just got 18. And then 0 minus 10, well, that's just -10. And then 6 minus 5 is just 1. So there we go. That is our vector. That's our representation of x here in the standard basis. Here's the final example, and this example is pretty similar to the very first example we did. Here we want to find the coordinates of this vector, which relative to the standard basis is given by 8, 1, 5, and we want to find the coordinates of that vector relative to this new basis b, which consists of 2 vectors. The first is 0, 1, 1, the second is 4, 0, 1. So just like before, here's the statement of what we want to find. We want to find the coordinates of the vector x relative to the basis b, and we'll say that that's just x1, x2. x1 tells us how many of b1 we want, and x2 tells us how many of b2 we want. Now, converting that into a statement about the vector in standard form, we have that the vector in standard form x is just equal to x1, the first component, times the first basis vector, then plus x2, the second component, times the second basis vector. And we can substitute the given information. X relative to the standard basis, that's just 8, 1, 5, so put that in here. And then substitute for the first basis vector, 0, 1, 1. Substitute for the second basis vector, 4, 0, 1. And here we've got an equation, a vector equation, and we want to solve that for x1 and x2. Like before, we can convert this into a matrix equation. On the right-hand side, we'll combine these 2 vectors into a matrix. 0, 1, 1 will be the first column, and then 4, 0, 1 will be the second column, and then that'll be multiplying the vector x1, x2, and we want that to be equal to the vector 8, 1, 5. And how we solve this kind of problem is we just convert it to an augmented matrix. So let's do that. So on the left side of our augmented matrix, we've got the matrix that's multiplying the vector. So 0, 4, 1, 0, 1, 1, and then draw a line, and then our resulting vector that we want it to equal to, that's 8, 1, 5. All right, so now we just want to use row operations to just get a diagonal of 1, 1, and the rest zeros. So let's go ahead and do that. So first of all, the first thing that we can do is in the top row here, we can divide by 4, and that'll just give us a 1, and 8 divided by 4 is 2. So now in the top row, we have 0, 1, and then 8 divided by 4 is 2. And then the rest of the rows stay the same, 1, 0, 1, and 1, 1, 5. And now we can eliminate this bottom row by subtracting these 2 top rows. So why don't let's first subtract the top row. So 0, 1, 2, 1, 0, 1, and we'll subtract the top row from the bottom row. So 1 minus 0 is still 1, but now 1 minus 1 is 0. Good, we're eliminating that 1, and then 5 minus 2 is 3. And now we'll subtract the second row from the bottom row also. So top two rows still stay the same, just like before. 1, 1, 0, 1. And now subtracting the second row, 1 minus 1 is 0. 0 minus 0 is 0. 3 minus 1 is 2. Great, so we've eliminated this row, and we just got ones and ones, and we can just switch these two rows. But wait, there is a problem here. This matrix is inconsistent. We've got a row of zeros here, but then there's not a 0 entry on the constant side. That's right, this last row actually corresponds to an equation that 0x1 plus 0x2 equals 2, or just 0 equals 2. Well, that's never true. So there's no solution for x1 and x2 that can satisfy the system. So no solution. Now, what does that mean in terms of the coordinates of a vector, though? There's no solution. What does that mean geometrically? Well, that really just means that the vector x cannot be represented using the vectors within the basis b. In other words, x is not in the span of b. There's no way that you can combine the vectors in v with linear combinations to yield the vector x. It won't happen. So that's our result. Our conclusion is that x is not in span b, and therefore there's no way to write its coordinates relative to the basis b. In these examples, we changed the basis of a vector by creating a system and solving it using the augmented matrix. In the future, though, we'll learn how to do this by simply multiplying the vector by a change of basis matrix.